research group is mostly interested in condensed matter in extreme spatial confinement, most prominently in very tiny pores, for example in nanoporous glasses. And on the one hand we are interested how fundamental properties like crystallization or flow properties change. On the other hand, we know that, for example, for water, there are drastic changes in these tiny pores, and this one can use to design new materials, for example, to store electrical energy or also to harvest energy from environmental processes. By wetting and drying of these materials, you can produce electrical currents, for example, and you can use these properties or this functionality in combination with tides at the beach to produce electrical energy in circumstances where, for example, there is no wind or there is no sun.
The SFB experiment offers us MHz imaging. So we can really shoot images of the membrane in a very, very short time scale. And it is very crucial for the transport in porous media of fluids how menisci and capillary bridges are forming and breaking during the wetting and drying process. And this process is usually so fast that we cannot resolve it in lab scale experiment or at the synchrotron. So from the X-FEL we hope to really resolve the drying and wetting and the formation of the menisci in the pores to gain more information about the time scales, the speeds, the contact angles and the mechanism and the properties.
Yeah, it's very important to know this in order to optimize these processes which I described before, this wetting and drying, and also to adapt the geometries of materials. So to tailor the materials in such a way that they work or function in the most efficient way, so that they harvest, for example, during this wetting drying process, the electrical energy with a very high performance.